To reverse a singly linked list, we need to return the head of the reversed list. This task involves changing the direction of the pointers in the list so that each node points to its previous node instead of the next one. By following a systematic approach, we can achieve this efficiently with a space complexity of O of 1 and a time complexity of O of n. We start by defining three pointers: previous, current, and next node. Initially, previous is set to null pointer because there is no node before the head, current is set to the head of the list, and next node is initialized as null pointer to temporarily store the reference to the next node during iteration. The core of the algorithm is a loop that iterates through the list until current becomes null pointer, indicating that we have reached the end of the list. During each iteration, we store the reference to the next node in the next node. This step is crucial because we will lose the reference to the next node once we reverse the current node's pointer. Next, we set the next pointer of the current node to point to previous, effectively reversing the direction of the link between the current node and the previous node. We then move the previous pointer forward to point to the current node, preparing it for the next iteration, where it will be the node to which the next node should point. Finally, we move the current pointer forward to point to next node, advancing current to the next node to be processed in the next iteration. By systematically reversing the links and advancing the pointers, we traverse the entire list and reverse the direction of all the links. When the loop terminates, previous points to the new head of the reversed list, which we then return. Consider a list with nodes head which equals 1, 2, 3, 4, and 5. Our goal is to reverse the list so that the nodes appear in the order 5, 4, 3, 2, 1. Here's how the algorithm proceeds step by step. Initially, previous is set to null pointer, current is set to the head of the list, node with value 1, and next node is null pointer. During the first iteration, we store the reference to the next node, node with value 2, in next node. We then reverse the link by setting the value in the node pointed to by current to previous, making the node with value 1 point to null pointer. Next, we move previous to point to the node with value 1 and move current to point to next node, which is the node with value 2. In the second iteration, we store the reference to the next node, the node with value 3, in next node. We reverse the link by setting the value in the node pointed to by current to previous, making the node with value 2 point to the node with value 1. We then move previous to point to the node with value 2 and move current to next node, which is the node with value 3. This process continues for each node in the list. By the time we reach the last node, node with value 5, we store the value in the node pointed to by current, which is null pointer, in the next node. Reverse the link by setting the value in the node pointed to by current to previous, making the node with value 5 point to the node with value 4. We then move previous to point to the node with value 5 and current to next node, which is null pointer. At this point, current is null pointer, indicating that we have reached the end of the list. The loop terminates and previous, which now points to the node with value 5, is returned as the new head of the reversed list. The algorithm runs in O of n time because each node is processed exactly once. The space complexity is O of 1 because we are using only a constant amount of extra space for the three pointers, regardless of the size of the list. This algorithm handles several edge cases efficiently. If the input list is empty, head is null pointer, current will be null pointer from the start and the loop will not execute, correctly returning null pointer. If the list contains only one node, the loop will execute once, reversing the link, which has no effect since it points to null pointer. And the function will return the single node as the new head. For a two-node list, the algorithm will correctly reverse the link between the two nodes, making the second node the new head and the first node point to null pointer. In summary, reversing a singly linked list involves initializing previous to null pointer, current to the head, and next node to null pointer. We then iterate through the list, reversing the links at each node and moving the pointers forward. When current becomes null pointer, the list is fully reversed and we return previous as the new head. This method efficiently reverses a linked list in O of n time, using only 3 extra pointers, maintaining O of 1 space complexity. This simple and elegant approach leverages pointer manipulation to reverse the list in place, handling various edge cases effectively, and providing a reliable solution for reversing linked lists. By iterating through the list and adjusting pointers, we successfully reverse the list while maintaining a clear and understandable code structure. This combination of efficiency and simplicity makes the algorithm a valuable tool for handling linked list operations in software development. Let's test the solution with different linked list sizes to ensure it works. Try lists of various lengths, including very short and long ones, to find any issues and handle edge cases. This will confirm the algorithm's reliability and efficiency in reversing linked lists.